Our next speaker, though, is very, very well known, and I'm sure you will appreciate his talk. My name is Steve Elsey. I'm with KRML Radio, and it's a real honor to be here. Welcome to the 7th iteration of Whalefest, Monterey. And I am not going to talk anymore because we were a little late getting started, but we're going to go over on this talk to make sure that you get the full flavor of Dr. Dan Costa down here from the University of California at Santa Cruz. Please give him a warm Whalefest welcome.
Hello, it's a pleasure to be here. And we were over lunch, we were just talking about the whole idea of working with an animal that you can't really see and follow. And sort of the way I open this talk is this picture is where most of our ability to study these animals is from the surface, from ships, from planes. And what I want to talk about today is how the technologies and tools that we use to go from that view of the animal to actually seeing what these guys do in real life underwater, and to see what they do, how they do it, and where they go. So the talk's going to be sort of, the outline is where we've started in terms of what we learned, what we knew when this whole sort of understanding through new devices and tools, how these new tools and technologies have given us new insights. Having worked with elephant seals over my entire career, having a field site that's 30 minutes north of our campus. We've done a tremendous amount of work with elephant seals, so I'll use them as a case study of a group of animals that we've been able to get tremendous insight into what they do. I'll talk about the ecology of the seals, how we can use them to study the ocean, and then I'll finish with a couple of quick views of some of the physiological studies that we're able to do, and end with what we've learned in terms of conservation issues. So, where have we started? I picked this year, 1967, because that was the year that a guy named Jerry Koyman actually published one of his first papers on diving behavior of Weddell seals. And if you look at what we knew at that time, we knew that animals got hooked on fishing gear. There was a sperm whale that was tagged in a transatlantic cable, so we knew that the only way it could have gotten snagged in a cable is if it ran into it. So these were the data we had on how deep animals dove. And I remember when I was a graduate student, this was still I was a graduate student in the late 70s, and this was still the data that we had on sperm whales. And so we figured, wow, these guys dive really deep. And then there was some little capillary tubes, which were, you just put a powder in a tube and see how far water would seep in, and that gave us some diving data on these animals. So really, we didn't know very much. And Jerry Koyman came on the scene. The reason I picked this particular individual is I finished my graduate work up at UC Santa Cruz as a graduate student there, went down to Scripps Institution of Oceanography to work with this guy, Jerry Koyman. And so previous to my working with him, he had already sort of started to ask questions of how do we study animals in the wild, how do we understand what they do, where they go, and how they do it. And for him, the new technology was, it's hard to tell, but this is an underwater housing that had a machinist make. And the guts of this thing was a kitchen timer that would go for an hour, and a Bourdon tube that was an arm would release as pressure, and a smoked piece of glass that was the pressure, the arm of the pressure gauge would scrawl across that smoked glass. So this was high tech back in 1967. But he was able to use this on Weddell seals, and the beauty of Weddell seals is they're used to living in an environment where they come up to a hole to breathe. And this is a natural hole, a picture I took of a Weddell seal. And Koyman used that to his advantage, where he would take a Weddell seal from the ice, on the ice, move it to an area where there are no other holes, drill his own hole. And so the animal had to come back and forth to a hole that he had developed for it. And the animal was actually, it was a natural laboratory, a situation where the animal was working on its own in the natural habitat, but he was able to get the animal to come back routinely. And so he really did some groundbreaking work. But, a 1-hour time record wasn't really enough. And so while I was a postdoc with Koyman, he had an engineer develop this time depth recorder, which just a beautiful piece of machining. This thing was machined out of a chunk of metal, out of a chunk of aluminum. It had a motor here. It had film, and this film would last 2 weeks, 14-day record. It had a Bourdon tube, so a helical Bourdon tube. This arm would then swing across the film, exposing it. As the pressure increased, the arm would swing out and swing back, and it would expose the film. Now, this was the state of the art when I was in his lab. This is a picture of that time depth recorder on an Antarctic fur seal. Back then, we used harnesses because it was a large device. We subsequently found out that harnesses actually created quite a bit of drag, so that wasn't really such a great way of doing it. The other thing about this is that when we ordered the film from Kodak, it came in a 9-inch spool, the guy would say, well, you know, there's one other organization, didn't say company, one other organization that uses this film. And it turns out, in hindsight, having seen some more recent stories about spy satellites, it was the same film that they used in spy satellites. And the reason they used it is the same reason we did, is so you can get as much film as possible on a little tiny spool. And so that was our first time depth recorder. You would get the thing back, and we would enlarge it onto a sheet of paper, and we'd run it down the hallway, and you'd sort of look at these dive records, and so you could see this is on the surface, and then that arm would swing back. And the other thing I didn't say is we'd have to put this thing together in a dark room, make sure we got the connections right, make sure that we didn't squeeze an O-ring, and we'd get it back, and we'd hope and pray that we hadn't screwed up and that the film would have worked, the batteries were still working, and the thing didn't flood. When you get this record back, these are 4-minute dives, and you'd sort of look at this thing. We'd have to hand digitize it. It would take literally 24 hours of digitizing this on a large platform, and that was our first time depth recorder. But it really opened up the world in terms of letting us understand what these animals are doing. This is an Antarctic fur seal around 1983. This is the same species. Now we have a satellite tag, an electronic time depth recorder, and a VHF tag so we could see where the animal's on the beach. And you can see that the technology is steadily improving. Today, we have a little tag like this that is only a few inches long. This tag has a temperature sensor here. It has a pressure gauge here. This thing has 16 gigabytes of memory. We can basically get a record from an animal diving at sea for up to a year. And all of those data are then downloaded via a communication port in your computer. It's all digitized, ready to go, and you can just analyze away. There's some other technologies that incorporate that little time depth recorder into a tag like this. That little time depth recorder is here. This now has a GPS position tag. This is another device with a GPS position tag. Both of these time depth recorders, position tags, transmit the information via satellite. So we can literally sit in our office, dial up to the internet, and see where our animal is, what it's doing, how deep it's diving, and get positions accurate to within about 50 meters. To show you how important that is, prior to these GPS tags, we used Argos satellites, and these yellow dots are positions of a California sea lion using just the Argos data. And for that same individual animal, these orangish dots are the positions using the GPS data. And you can see that the yellow dots are all over Monterey Bay. And if you sort of look through that, you'd realize that you would completely miss the fact that that sea lion was doing something in association with the Monterey Canyon, with a limb of the Monterey Canyon. And that it really was sort of moving between Santa Monterey, Moss Landing, and the canyon. If you just had the yellow dots, which are the standard Argos location data, you really wouldn't have anywhere near the idea of what this animal is doing. So this just gives you an idea of, in a short period of time, how much the technology has changed and what we're starting to learn. So that's sort of our little quick history lesson. Now I'd like to say, okay, well, let's take a real look at what we've learned about these animals. What are the new insights? What did we not expect? And one of the big things is, here we have a male northern elephant seal. One of the big things is we learned that you can just use 5-minute epoxy to glue these tags to the hair. And that really is an amazing thing. It's just really simple to put these tags on. It doesn't bother the animals. and the tag will fall off within a year because they molt every year. So you know the tag's not going to stay on any longer than a year. So if you don't recover the animal, can't get the tag off, it will fall off. So what did we learn? Well, the first thing is when we put these satellite tracking devices on, we realized that the animals went to places we had no idea. If you looked at in 1991, before we did these tracking studies, this was a book that Marianne Reedman, she was at the Monterey Bay Aquarium, she wrote about pinnipeds, and this is where we thought northern elephant seals were distributed, from Baja California, because we knew there's breeding colonies here, up to Vancouver, and we thought they had this nice coastal distribution along the west coast of the U.S. And the reason we had this idea is because this is where we'd look for them. We'd fly a plane or drive a boat, and we'd census this area, and so this is where we saw elephant seals, because this is where we looked for them. But if you ask an elephant seal to tell you where it goes by putting a satellite tag on the animal, and we put tags out at Año Nuevo, and then we put tags out on San Benitos Islands in Mexico, you find that they range over the entire North Pacific Ocean. So just this technology changed our view of the world and gave us a completely different idea of what these animals do and what they're about. So just to give you an idea of what these animals are doing, there's a little animation which hopefully I got it running. Yeah, here we go. Right, so the longer the track, it means the animal is moving rapidly because it's covering, for the same period of time, it's covering, it's about a 7-day track. When these are really small, it means the animal is staying in one area. So each one of these is an individual seal. They're going and coming. So they're going out. These are female elephant seals. They have a short trip after the breeding period. They go for 3 months. They come back and molt. Then they have a long trip. This would be the long trip, which is about 8 months. Then they come back to breed. And so they do two trips a year. And these are a series of trips. Each one of these, for every 2 trips is a year. So this is several years worth of tracking data. Since 2004, we've been putting tags on about 20 females through every one of these cycles. So we now have something on the order of 500 tracks of northern elephant seal females, and we're getting a tremendous amount of information about what they do and where they're going. So that's what they're doing on the surface. If you look underwater, here's the dive record. This is the surface. This is 800 meters. That's about 2,400 feet deep. The maximum dive that we've seen for elephant seals is 1,730 meters. That's over a mile deep. On average, the animals are diving 516 meters, but they really have a bimodal distribution. These are dives at night. These are dives during the daytime. So at night, they're going about 460 meters. During the daytime, about 620 meters. That's pretty deep. Multiply that by 3, that's almost 2,000 feet, and that's about 1,500 feet of water. So these animals are working in what we call as the mesopelagic zone of the ocean. This is a very poorly understood area of the ocean where there's a lot of these interesting lanternfish and deep-sea fish, which recent studies have indicated that just our estimate of how much food is there is off by at least an order of magnitude. So that's where they feed. They're feeding on these deep water squid, deep lanternfish, and these very interesting, often very bizarre-looking fishes. The other thing to notice about this record is this starts on August 25th. It goes to August 29th. This is just one section of a 8-month track. But if you looked at another 2-week period or a week period, it would look the same. These animals basically don't stop diving. When they're at sea, they're working nonstop, about 20 minutes underwater, 2 to 3 minutes on the surface. So they're literally diving machines. Now the longest dive we've recorded is about 1 hour and 43 minutes, which is pretty amazing if you think about it. What's even more incredible is this really long dive was preceded by 1 hour and 9-minute dive, 1 hour dive, 51-minute dive, 1 hour and 43 minutes, 1 hour and 10, and 59 minutes. And there's a 2-minute surface interval. So these animals, over this period of about 8 or so hours, probably spent all of about 10 or 15 minutes on the surface. We don't know what was happening, why this animal made these really long dives, but this pattern suggests that something happened that made the animal want to avoid being at the surface. So was there a predator? Was there a killer whale in the area that it heard? Was it really unusual weather? We don't really know what was going on. What we do know is this was the longest single duration dive, and the dives are reasonably deep, but for elephant seals, we think that for them safety is in the deep ocean because they really don't like being at the surface, and this series of dives makes that point. Now you might ask me, how did they do this? And that's a really good question. We don't really know. We can figure out that the 20-minute dive with a 2-minute surface interval, our understanding of the physiology of this animal kind of works. They have large oxygen stores. They have what we call an internal scuba tank. How they do these hour and 43-minute dives, we can figure out how they do one dive, but most of the studies we've done would suggest in something like a Weddell seal, if you did a dive like this, you'd have to spend the next 6 hours sitting on the surface paying back an anaerobic debt. So how these animals can do these dives one after another, making these extremely long dives, is something that we really have yet to completely sort out.
Is that common? Is that something you saw in your data on a regular basis, that length of dive?
That is the longest dive, and it's very unusual. So it's not uncommon to see maybe an hour dive and maybe a 50, 60-minute dive, but even those are rare. The majority of the time, the dives are 20, 25 minutes. So that is the most unusual record. That's the Olympic record for elephant seals in terms of how long they can dive. So yeah, that's a very unusual dive. But we still can't completely explain how they do it. And it is an extreme case, so that whatever they're doing, they really are pushing their physiological capability to the absolute limit. So one of the things we did is when you get these records, you see these dive patterns, and you start to say, well, this looks like the animal's feeding, that it's moving up and down in the water column, it's sort of diving around, feeding. And so we sort of started to convince ourselves that those are in fact feeding dives. What was interesting is we'd get these feeding dives would be followed by dives where the animal would go to a certain point and then drift. And we knew it drifted because we put swim velocity and accelerometers on. And we know that the animals go to this point and literally just drift through the water and then wake up. Well, we don't know if they're sleeping or not, and then swim up. And so these dives, we think, are processing dives. Whatever it is, the animals don't like to be at the surface. So just like after a big meal, you get tired and you want to sit back and sleep and get groggy, we think that elephant seals are moving the oxygen they use to fuel the metabolism to swim. They're moving that oxygen from the muscles, the swimming muscles, to the digestive tract to allow them to process the food. So that's what we think is happening during those dives. And the beauty of a dive like that, and here's a close-up of a single dive, is you can see the animal swims to a point and then stops swimming and then just sinks. And then it turns around and swims up to the surface. Now, what's cool about this is if the animal is drifting, it gives us an idea of what the animal's body composition is. That if the animal is very lean, it's going to be thin, it's going to sink rapidly. On the other hand, if the animal's really fat, and we actually see dives like this where the animal goes down to a point, instead of sinking, it actually floats up. So this gives us an index of how fat or lean the animal is, and we can go through a dive record and look at whether the animal is in this state where it's skinny or this state where it's fat, and we can start to figure out, okay, the only way it's going to get fat is if it's feeding. So what we did is we've gone through our records and we're able to generate a map of the North Pacific showing where these drift dives are occurring, and where that says that if we are in fact processing dives, it means the animals are metabolizing or digesting their food. And we can also then tell where it is in the ocean that the animal's getting most of its food, where it's most successful. And this region, we'll see time and time again, becomes very important. You can see here that the animals are not doing a lot of drift dives. This is where the animal is transiting. So it's coming from Año Nuevo or from Mexico, swimming out here into the North Pacific, and this is where it's getting most of its food. It's way out there in the middle of nowhere. Now that seemed pretty good, but it didn't. That gave us sort of on average what the animals were doing. And along comes our Japanese colleagues from the National Institute of Polar Research in Tokyo, Yasuo Naito and a number of his students. And they came with these little tiny accelerometers that we can glue underneath the chin of elephant seals. And we've calibrated these accelerometers so that they tick every time the animal has particular acceleration that's associated with jaw opening and closing when the animal's chasing fish. And we did that because in the laboratory we took animals into the lab, put these accelerometers on them and fed fish and saw what the characteristic signature was that is associated with jaw movements that are the animals catching fish. And if you then plot these, you can see the red dots are every time the animal is going after a fish. Here's a 3D representation out in the North Pacific. Here's time on this axis, depth. You can see that most of the jaw movement and feeding is happening at the bottom of the dives. We do see a few events that are not associated with the bottom of the dive, but the majority of the feeding behavior is at the bottom of the dives, just like we thought. So this really kind of reinforced our understanding. The other thing is notice these drift dives, these processing dives, there's no feeding. And again, these processing dives are associated with after the animal's been doing a lot of feeding, it's time to sort of digest and process that prey. And in this figure, you can see those processing dives, you can see the feeding dives, more processing dives. You can see that pattern sort of intermittently through the track of the elephant seal. And you can see the sort of up and down movement as the diurnal pattern that these animals are following that vertically migrating prey. So that gave us real confidence that we, in fact, are following these animals where they're, in fact, feeding. And then, again, our Japanese colleagues, which have been a tremendous collaboration over the years, moved from these little jaw accelerometers to cameras. First still cameras and now video cameras. And so there's one little clip here which shows you the ocean from the camera as it is glued to the animal's head. And you see very quickly come by, let's see if we can do that again, a fish. So this is the world of an elephant seal, seeing what it does and what kinds of fish. Now we've got really interesting images of squid that they eat, a variety of different fishes, and some images of things that, as you can see, it's a glimpse. They're often quite difficult to sort out. But this technology keeps pushing back the window, as I say, pushing back the curtain and giving us insights that we couldn't have had any other way. I did my doctoral work on sea otters, and for sea otters, figuring out what they feed is easy. You sit on the shoreline with a pair of binoculars, and you just look, and you say, oh, he's eating a crab. Oh, now he's eating an abalone. Well, we don't have that luxury when we're working with animals like this, so we have to do all kinds of interesting tools to figure it out. Now, again, putting these technology of the track of a female elephant seal and putting that into context, especially in Google Earth, where you can now plot these diving records in association with the ocean bathymetry. What's interesting about this is this female really liked seamounts, and we tracked her 2 years in a row. And the first year she went out here and she spent a lot of time foraging on this seamount, and then went on to this seamount, and then eventually came back. The next year she went out there, she went to the seamount, spent a few hours, and then moved on. So whatever was there the year before, it wasn't there the year she came back. Now, I've mostly showed you female tracks, and some of the early work we did is we showed that females in yellow and males in red. So that's a male and that's a female. Males are much bigger than the females. They have very different foraging patterns. The females, the males in red are feeding up along the Aleutians, up along southeastern Alaska, and basically seem to go to the edge of the continental shelf. Females, on the other hand, really like it out here in the North Pacific, out here in this area where it's the features in the ocean, the habitat is associated with water masses, with the moving of currents. The males seem to like features that are associated with bottom contours and the continental shelf break. One of the things we first did early on is we just left the tags on for an entire year, so the males would go out, forage, come back. We left the tags on, and then they'd go out and forage again. And when we did that, you can see, well, you probably can't see, but there are two tracks here. So here is a male going out to the Aleutians, turns around, comes back, and if you can see the dotted lines, the second trip is right on top of the first trip. And you can see, again, a different individual, again, a different individual. So these are two independent tracks, but the animal basically, almost like he has a GPS tag showing him where to go. How they do this navigation, we're not really sure. We think that magnetic sense is part of it, but that's, again, an area where we have yet to really sort through. One of my favorite stories is a female that we tagged in 1995, and my students were out in 2006 looking for 6-year-old females. They read the tag wrong and put a tag on a 17-year-old female. They thought she was a 6-year-old. We normally wouldn't tag a 17-year-old. But what's even more amazing is that female that they misread the tag was a female that we had tagged 11 years earlier. So this is a tag of that same female as a 6-year-old in 1995, and then as a 17-year-old in 2006. So this, we don't know if she's doing the same thing for the last 11 years, but it certainly is suggestive that she was probably doing the same thing year after year, because for 11 years later, we took and found out the female was in fact doing what she did 11 years earlier. I like this story because it was complete. I mean, what are the odds? We didn't tag that many animals. We tagged maybe 15 animals in 1995, 96. The fact that we would accidentally put a tag on her because we read the tag ID wrong. So this, because as I said, we've now got something on the order of 500 tags, and there's only 2,000 elephant seals, females, that breed every year at Año Nuevo. In the course of doing that, you're going to put tags out on a lot of individuals. And one of the things we've started to do by just going through our database, we've recognized that we have tags of a mother, of a female, and then we have a tag of her adult daughter. So these are tracks of a mother and her daughter. So this is the mom, and this is her daughter when she was at least 6 years old. And we're starting to ask the question, how much of the track, how much of where these animals go is programmed genetically? Because these animals don't go to sea with mom. Mom leaves the pup on the beach. The pup has to figure out how to be an elephant seal on its own. So if these patterns continue from all the animals that we have got, both tracks of mothers and the daughter, we can start to assess how much of this track might be sort of something that's intrinsic. Now, I've been talking about elephant seals, and since this is Whalefest, I thought it'd be interesting to then give you some insight into some of the other things that these tags are telling us about cetaceans. And in this case, for the longest time, we were sort of lucky, well, I'm not sure lucky, but elephant seals were the king divers. And then Sasha Hooker and Robin Baird came along and put a time depth recorder, that little one I showed you early on a beaked whale off Canada, and they came back with a dive record that looks like this. And this really even makes an elephant seal look like a slackard, because these animals are diving routinely between 800 to, 1,400 feet. The dives are routinely on the order of an hour or so, and these animals are just knocking off one dive after another. Now, what's amazing is this was the first time depth recorder deployed on a beaked whale, about 18 years ago. Beaked whales were the most unknown animal, and one of the ways I talk about how unknown they are was we still are finding new species of beaked whales. How is it that you have an animal 30 feet long and we're finding new species of it? That tells you how little we know. But because of a lot of interest in beaked whales, because they're deep divers and because they've been associated with mass strandings from seismic surveys and naval sonar, there's been an incredible amount of research that's been done over the last 10 years. And we now know probably more about beaked whales than certainly any other cetacean. If you go to certain areas like off the Bahamas or in the Mediterranean or off the Azores, there are places where beaked whales are very common, and you can actually approach them and put suction cup tags on them. And one of the things that I think is really cool, I showed you all the things we had to do to figure out how elephant seals feed. Well, early on when they put these tags out on beaked whales, they put an acoustic listening device on, so they could digitally record the sounds that both the beaked whale made as well as the sounds around the environment. And so that's the tag that is both a time depth recorder and an acoustic receiver. And what they realized is that as the animal would vocalize, they could get that vocalization, the sound of the animal, but they'd also get the echo off of the food, off the squid or whatever it was that the beaked whales were feeding on. And so they could start to understand when the animal caught prey and how it would actually sneak up on prey, or maybe it doesn't sneak up. But here's the echo. So this is very loud sound. This is time on this axis, and this is distance in meters. And you can see that here's the sound being produced by the animal, and this is the echo becoming, it's very faint out here. It's getting louder and louder, but it's getting closer and closer. So that echo is getting, the distance between when the animal makes the sound and the echo is very close as the whale approaches the sound. So these are the individual clicks of the animal, the echo, and then as the animal gets really close, it goes from a click to a buzz. So it's click, 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 zzz, and that buzz is helping it hone in the last few meters just before the animal then captures its prey. So you can see the animal accelerating, going up, and capturing that prey. So this again was sort of they were interested in studying the sounds of the animal or the environment, and this was an added bonus that they're actually able to measure when the animal captured prey. Now the other thing is I sort of made a big deal about how great it was that we could glue our tags onto animals. That's a really big deal because studying cetaceans, they don't have anything that is so easy to put something on them. People use suction cups, but suction cups last for like 12 to 24 hours and then they fall off. So for us, we just go out, put some 5-minute epoxy, the tag stays on for months to a year. Well, there's been a lot of work figuring out ways of putting on a tag that could last more than a few hours. And the most recent thing is this LIMPET tag, which stands for Low Impact, Minimally Percutaneous External Electronics Transmitter. And the tag looks a little, ugly in some respects, but the beauty of this tag is that you can shoot them with a bow and arrow, and it typically will go into the dorsal fin. So the idea is to shoot it into the dorsal fin. They've done a lot of studies to figure out, in this case it was a thermal image to see if there was any sort of wound or healing or issues associated with the tag placement. They've run these things through hydrodynamic simulations to try and get the size and characteristics. The good news is these tags will last up to about 3 months or so. And it's really opened up a new world in terms of small cetacean or medium-sized cetacean tracking. And this is one of my favorite stories. I had nothing to do with this. I think it's just a really cool story. This group working in the Antarctic on killer whales put these tags on killer whales in Antarctica, and they tracked them from the Antarctic Peninsula, and these animals would be down there feeding, and all of a sudden they'd make a beeline to the subtropics. And so here's an individual that made a beeline to the subtropics, went up to where it's warm, then turned around and came back. And so there's a number of these tracks, and increasingly they're getting these tracks. One of the things they noticed is when the animals, just before they would leave, they look kind of dirty and gungy. And this isn't actually a nice clean killer whale. But they get this sort of greenish tinge to them, greenish-brown tinge, which is algae that was growing on them. And when they'd come back after going to the tropics, they look like this, and all nice and clean and ready to go. What we think is happening is that killer whales, remember, they have living tissue. Their skin, as in any cetacean, their skin is exposed to the environment. And we think that they can tolerate that, but only so long. And what they're doing is taking a mini vacation to go and warm up and probably rejuvenate and reconfigure their skin before they then come back to the Antarctic to continue to feed. At least that's what we think is going on. And it certainly makes sense that given that this is a pretty cold environment and the fact that this is living tissue, that they periodically go to sort of warm up. Okay, so I've given you some examples of what we've learned about elephant seals in particular, and sort of a few stories about how this sort of technology is moving into the cetacean world. I'm now going to tell you a little bit about what we're understanding about the environment, the habitat that these guys live in. And I'm going to talk about seal ecology, but I'm also going to talk about how we're using seals as oceanographers. And I put these arrows because it's a two-way street. is as we learn about the oceanography, it tells us about the seal's habitat. As we learn about the seal's habitat, it's creating data that we're able to use to understand the ocean in its own right, the sort of the physical and biological oceanography. Now, I mentioned that there's this region that the elephant seals keep coming back to. And if you look at the North Pacific, this is sort of a real quick cartoon. There's the ocean currents go this way, so the water comes across the North Pacific and then creates the California current here. The water comes across and then bends up, creates the subarctic gyre, the Alaska coastal current. And this feature here is a gyre boundary that sort of separates this colder subarctic water from the warmer subtropical water. And there's a major temperature gradient right across this feature where these two water masses meet. And then there's this feature called the transition zone chlorophyll front, which is sort of like the Serengeti, the grasslands of the North Pacific. So that's the general pattern of the oceanography. And what's interesting is if you look at where elephant seals feed, remember I said here's this region where we know that they're feeding. This is that boundary between the cold and warmer water masses. This hotspot is where most of the elephant seals, it's called the kernel density plot, so this means there's a lot of seals here, not so many here. And that's the feature that the elephant seals seem to like. Now the other thing we can do is if you take a track of an elephant seal, a single animal that sort of went across this feature here, we then plotted that out. So here's depth on this axis, and this is distance. So this, if you draw a line across here, that's essentially what we've done here, is draw this line right through there. This shows temperature, so this is warm water, cold water. This is sort of showing that demarcation. You can see this feature here is right about there where you go from transitioning from warmer water to colder water. You can see there's some very interesting structure to it under the ocean. And this shows where are the elephant seals. So at the time that these data were taken, this is where most of the elephant seals were. Early in the year, this dynamic feature is a little different. Again, colder water, warmer water, you can see that transition. And the majority of the seals are associated with where that temperature change seems to occur. So again, we're starting to understand the habitat of these animals in reference to where they are in the ocean. And this just shows another feature. These are eddies, sort of cyclones in the ocean. And this female elephant seal really liked, she would like to go and spend her time feeding in these large cyclonic regions in the North Pacific. Now the other thing, as I said, we have those temperature tags. Here's that cyclonic feature. The animal's tracking through that area. We take that transect, and this is temperature. That's warm water, cold water. We would call this a downwelling eddy. That is, the water from the surface is being pushed down into the ocean. You can see that the warmer, this is cooler here, but that warmer water is being pushed into depth, sort of that we can sort of document the characteristics of that feature. And these structures are very important when you're trying to understand something about the ventilation of the ocean, the CO2 budget, a lot of the things that physical oceanographers are concerned about. Some of you may remember hearing about the North Pacific blob, this large mass of warm water out in the North Pacific. Well, that's this warm blob. This is a sea surface temperature map that we just got by dialing up the NOAA database. But what I'd like you to notice is that these are elephant seal tracks. And so our elephant seals are going through this region of the North Pacific, and we have multiple females that have gone into this warm blob. We have this one female here who went into that area and then said, I don't like that, and left. Here's her track in 3 dimensions. You can see the individual transects as she's diving. You can see colder water, warmer water. You can see that she is sort of documenting the depth and characteristics of that warm water feature. And we're now starting to take these data. One of my graduate students is using the elephant seals to characterize the depth and characteristics of that warm mass that was out there in the North Pacific. Now, there are other ways that oceanographers have of measuring these features. They have Argo buoys. These are floats that go out and go up and down on their own. These things float around, and so they're not going anywhere in particular. These are the positions of those Argo buoys in 2014, 2015, and these are where the elephant seals go. And the beauty is that the elephant seals, for whatever reason, we don't know what that reason is right now, are tending to go into that region where that big warm water mass is. And so the elephant seal data are going to certainly complement the more traditional ways of measuring these oceanographic features. So I've told you about seal ecology, oceanography, and I'm going to give you a real quick glimpse of some of the things we've been doing in terms of understanding their physiology. And the other thing about this story is that we're a niche market. It's not like Apple or some company is going to build us a device that does exactly what we want. And so you got to get really clever about taking off-the-shelf technology. And so you know those polar exercise things you can measure heart rate in? Well, we figured out how to take those devices, put them in epoxy to waterproof them, make electrodes, and use them to measure the heart rate of an elephant seal while it's at sea. So here we have the diving record, which you've seen lots of. You can see something interesting happened here where the animal went deeper, sort of a typical dives, then all of a sudden it went deeper. Well, interesting enough, its heart rate also changed. The other thing to notice is that at the surface, the animal is going about 100, 120 beats per minute. When it does these dives, its heart rate drops to about 40 to 50 beats per minute. And in some of these longer dives, we've actually got animals having heart rates of down to 4 beats per minute. So this is, again, this is kind of what we expected. There had been lots of previous studies in the laboratory, but very few examples where we could look at what an animal that's in the wild doing its own thing, how its heart rate varies over the dives. And sort of just taking this off-the-shelf technology and adapting it for use in the seals has been a big plus. Now, there are some devices that are very difficult. You basically have to sort of bite the bullet and just come up with some other way of doing things. Paul Punganis, who is a colleague at the Scripps Institution Oceanography, has been working on creating some really sophisticated devices. And in this device basically is a spectrophotometer that measures with fiber optically measures the color of the blood. So we have an indwelling catheter that goes inside the animal. Gita McDonald is now in the faculty at Moss Landing Marine Lab. She was a postdoc working with Paul. Corey Champagne was a graduate student of mine at the time, so getting this device ready. And what they were able to do is here's the dive pattern of an elephant seal. So we took this young elephant seals that we can move around. We drive them down to Hopkins Marine Station with this equipment on them. We would then look at their diving pattern, and here we have now their blood oxygen levels. So this is the blood oxygen in the animal during a dive, and it runs down to 3 milligrams of mercury. And if you were to say, well, who cares about 3 milligrams of mercury? 20 is where we would black out. So if our blood oxygen level dropped to 20, we would be unconscious. This elephant seal is merrily working its way, continuing to do a dive with its blood oxygen almost completely gone. And so this work is ongoing. This is a record now where we've taken the animal from down here at Monterey, and it's swimming back to Año Nuevo. You can see that there's lots of oxygen in the blood during the dive. That oxygen sort of goes away to where just before the animal is surfacing, that oxygen is almost completely gone. It comes to the surface, reoxygenates. So you can see this record of an elephant seal where we've now looking at how its physiology changes over an entire trip to sea from dive to dive over that period of time. And just as an interesting aside, the gal that did this work was a graduate student with Paul Punganis, Jessica Meer. She's now an astronaut. In the last round of astronaut corps, which was, I guess, about 2 years ago, she's trained as a comparative physiologist. She was the most recent addition to the NASA astronaut corps. I always kind of get excited about that. Okay, finishing up, I wanted to tell you that we have done some things with these kinds of tags that are important for understanding how to keep these animals on the planet and how to preserve them and conserve them. Some work that I've been involved with was in Australia, working with the Australian sea lion. And one of the things is that this population was It's an endemic. There's less than 10,000 individuals. I could go on and on about Australian sea lions. But the story here is that there was a shark gillnet fishery. And the sad thing about this shark gillnet fishery is it tended to catch, incidental to the shark catching, they would catch adult female Australian sea lions. And so the question became, well, how important is this fishery? We knew, as you can see from these pictures, that they were catching sea lions. But then the question becomes, well, what can we do about it? And what we're able to do is tracking these Australian sea lions. This is one of the two major colonies, about 200 individuals here, about 1,000 individuals here. We're able to show that the animals feed on the continental shelf. So these are depths in meters. So the animals are no diving deeper than about 120 meters. And most of the diving for food for their youngsters is associated with the colonies. We then took the gillnet fishery and looked at where the gillnet fishery was occurring. And then you could see where you put the two together, and you could see there's major significant overlap between the shark fishery and the Australian sea lion colonies. And what we're able to do is basically say, first of all, we know where the Australian sea lions are. We can make marine protected areas associated with these colonies. And more importantly, we could say that if you fish below 120 meters, you won't catch any sea lions because they don't feed there. Because they're on the continental shelf, anything deeper than 120 meters, the animals will not be there. And so if you're able to have a fishery beyond 120 meters, you can do that. Anything shallower than that, you're going to likely catch a sea lion. The end result is that there was other issues with the fishery, and at the end of the day, they finally closed the fishery. And the good news for the sea lion is that they are now able to recover. Locally, we've had an impact. This was tagging of Pacific predators. A group, Barbara Block and I at the Hopkins Marine Station, put together a large tracking program of 20-some-odd species. In this figure, a graduate student of mine Sarah Maxwell took all the air breathers, the sea lions, and some of the seabirds, whales, and plotted where we find them in terms of using all these tracking data. Where in our tracking data do we find them, and then mapped onto that the various national marine sanctuaries. So the Channel Islands National Marine Sanctuary, the Monterey Bay Sanctuary, and the Gulf of the Farallones. And you can see that the sanctuaries actually do overlap with a fair amount of the range of these species, which is the good news. The other thing is our data were used in arguing for, at Congress, it never happened in Congress, Obama made an extension, maybe you remember, an extension of the Cordell Bank Gulf of the Farallones National Marine Sanctuary. We were able to show with our tracking data that while the current sanctuaries cover a fair amount of the range of these air-breathing vertebrates, there's a lot of area that is not covered, that could be covered, that is a very extensively used region by these air-breathing marine vertebrates. And so we're glad to say that some of our data was helped in pushing for that extension of the sanctuary. So hopefully you've come to see some of the things that we're able to do, how the technology is really opening our eyes and giving us an insight to what these animals are doing, and also beginning to give us some better conservation tools. Thank you.